So, the history. I started building a project called aka.net in late 2013. And aka.net is a framework for concurrency and distributed computing. And any distributed software needs some way to communicate between nodes. So, of course, we need some sort of serialization mechanism between the nodes. Since every message that you need to pass needs to go from an object model into bytes onto the wire and then back again. So, the requirements we had is that we need to be able to preserve type information. For example, let's say that I want to serialize an array of objects containing 1, 2, 3 and hello, for example. In this case, 1, 2, 3 would be an int32 and hello would be a string, but the array here would be an object array. That might not sound very strange, but we'll look at the alternatives later in existing serializers and see what happens if we use, for example, JSON.NET for that. We also needed to be able to preserve object identities. Let's say that you have an object which refers to itself or refer to another object which then refers back. So when you deserialize, you don't want to have this graph of decoupled objects. You want to have the same object identities when you deserialize. A really tricky problem that we had to solve was context-aware objects. For example, in aka.net, we have the concept of an actor reference, and each actor reference is bound to the actor system they belong to. So when you deserialize an actor reference, we need some way to take the deserialized object and then reattach it to the receiving actor system and say, well, you belong to this actor system and you refer to this actor somewhere. Polymorphic types. If you have an object with, let's say, an animal property, and then you create an object of type dog, then you probably want the object in the deserialized side to actually be of type dog and not just animal. Another sort of tricky requirement is exotic types. For example, F#. In aka.net, we have this special API for F#, which is streamlined to be functional. The problem is that F# has sort of its own type system built on top of .NET. So it has the concept of discriminated unions, and it has its own special list types and all sorts of tricky types. And none of them are built for serialization. So it's sort of hard to take these objects and then turn them into a byte representation. Another problem is version tolerance. Let's say that you serialize an object, put it into a database or to a message queue, then you probably want to be able to deserialize it again, even if someone had made a change to the schema of the type. And the last property of the requirements is we need it to be fast. Since it's a framework for distributed computing that we are building, we need to be able to send as many objects as possible in the least amount of time. Why doesn't my keyboard work? So, what options did we have? We did look at protobuf, but protobuf is a really fast serializer, serializer built by Google. The problem there is that it can't handle context-aware objects. You can't take a protobuf object and then magically reattach it to some sort of context when you deserialize it. And also, it's not built for handling exotic types. You can't make a protobuf schema and then turn it into F# types. There is no adapter for that, at least not one that I know of. JSON.NET, the absolutely most common serializer in the .NET stack. It sort of works, and that is what we have as a default serializer in aka.net right now. And the problem there is that JSON is not built for keeping type information, really. In JSON.NET, there is an option where you can say that, well, I need the type name persisted into the JSON document when you serialize. So let's say you have an object of type dog, and you serialize that, then you can make JSON.NET have a property called $type, which contains my namespace .dog, for example. So it works for objects, but it doesn't work for primitives. For example, if you serialize an integer, there's no way to distinguish this integer in the JSON document from a double or from a long or whatever, because it's just numbers in the JSON document. So when you deserialize, if you don't know the type of it, it will just deserialize into whatever type you think fits. So you could very well, like in this case where we have 1, 2, 3, let's say that this was an int32 when you serialize it. It will actually deserialize as a double, just because it doesn't know what type it should be if it's inside an object array. Then there's a bunch of other serializers in .NET, and most of them are specialized for certain concepts. Some are specialized around version tolerance, some are specialized around JSON, but none of them really fit our needs. We need all of these requirements. So JSON.NET was the one that took us closest to this list, but in order to do so, we had to abuse JSON.NET quite much. So it became quite slow because we had special adapters for pretty much everything we wanted to do with JSON.NET. So the solution, and this is what Jonas has been nagging me about, asking why would you write your own serializer? Well, if none of the serializers out there actually fits our needs, then there's really nothing you can do but write your own. So how hard can it be to take an object and turn it into bytes? It should be sort of easy. So, but this session will be about performance. And in the invitation, I said building Wire, the fastest .NET serializer for .NET. So how fast is fast? And when I started writing about this, Greg Young, who sort of coined the term CQRS and have been promoting event sourcing, he was sort of pushing me and saying, can't you include a benchmark of some manual serializer? If you just take some manual code, that will of course be the fastest code for serialization. So he had this old blog post written somewhere 2010 or something, where he actually wrote about fast serialization. So had this sort of concept where he could manually serialize an object where you just had to provide this write data and set data methods. So this should be the fastest way to actually serialize an object, right? Because if the only thing you do is take each property, take the value, put it onto the stream, take the next value, put it onto the stream, take the next, do the same, it can't really be any faster, because that would require some sort of magic, right? And the same thing for reading the object. You just take the stream, you pull some bytes from it, put it into the object, pull some more bytes, put it in back to the object. So if we actually look at some metrics, here I have Excel, and at the top we have Greg Young's custom serializer, serializing 1 million objects in 636 milliseconds. The funny thing was that Wire actually performs at this speed, so it's a good 25-30%-ish faster. So I think it will be kind of neat to see how we can do that faster than writing this manual super slim code. But let's start by looking at these numbers. We can see that there's a bunch of different serializers, and then I have a tab in Excel for different type of messages. So this is not a selective benchmark because we have tried to serialize different objects. So the first object we've serialized is a Poco object with 4 properties. It's an int property, a datetime, a GUID, and a string. Sort of the standard kind of message type we have in aka.net. So we can see that Wire does this in 453 milliseconds, and that means serializing and deserializing 1 million of these objects. And if we take JSON.NET, which is the sort of standard serializer in .NET, we can see that it's more than 10 times as slow. And if we take the old binary formatter from built into .NET, it's insanely slow compared to the rest. I should also say there are some serializers not included in this list. For example, Microsoft has this serializer called Bond, which is also sort of fast. It's topping in somewhere around 3 or 4, but it's not really a general purpose serializer because you need to define these schemas, and it actually was unable to serialize the messages or different types we had in its test. So it succeeded in some tests, but couldn't serialize most of the other tests. So, but just so you know, it has been benchmarked and it was somewhere 3, 4, 5. And the different columns, the first one is total round trip, which is serialized and deserialized together. And the second one is just serialization. Third one is deserialization. And the fourth one is the payload size. How many bytes does a payload turn out to be? Because that is also an important factor. Even if you're super fast, if the payload is really big, then your application will probably be slow because you need to sort of move a lot of data over the wire. We have some different types. Why isn't the zoom set to the same? The same object but serialized inside an array. We can see that wire is still the fastest. And we can see the benchmark graphs here also, that wire with different settings take all the top positions: NET Serializer, protobuf.net, NetJSON, binary formatter is super slow. So we don't have to go through all of the different types of objects. They are on GitHub. You can download the actual project and run the benchmarks for yourself to see. Here we have serialized 1 million GUIDs, so it's also performant on just primitive values. So apparently we can be faster than this code. And if you benchmark with a profiler how wire actually performs, I guess you can't really see exactly what's on the screen here. The green part of this bar is system.io. It's a memory stream that we are serializing to. And this gray part, 35% of the CPU time, is actually wire. The rest is system types and the streaming abstraction. So during this 450 milliseconds for serializing 1 billion objects, of that time only 35% is actually wire time. The rest of the time is .NET itself. So let's look at some code. The basic architecture of wire is, first we have the serializer type, which is sort of the base of it all. It's on the serializer that you call serialize and deserialize and whatever. We also have this serializer session and deserializer session. These contains lookups for each serialization or deserialization calls. So you have these lookups for what types have we already deserialized, what schemas do we know about, etc. And that those buffers are filled as you deserialize or serialize objects. We also have the code generator, which is responsible for emitting .NET code at runtime. Then we have the most important parts, the value serializer and the value serializer factory. The last one sounds a bit Java-ish, but it's actually a factory. So the value serializer is a sort of small serializer for a specific type. We have one value serializer for int32, another for int65, 64, etc. So we have a specific value serializer for each type that we know about up front. But of course, we can't really know about every custom POCO class that you have in your system. That's why we have the value serializer factory. So we can see if there's a type that we don't know how to handle, then we could create an instance of one of these value serializer for your type. We will build a new serializer on the fly for you, which can be reused for the rest of the lifetime of the serializer. And also important to know is that we need a schema, and the schema for wire looks something like this. When we serialize an object, we first need to write this manifest saying what kind of type it is in the byte stream. And then we also need the object payload. So the type manifest is telling the serializer this is what you're going to deserialize, and the payload is actual content. Then the schema can be recursive. So if you have a POCO containing other POCO classes containing more POCO classes, then it will recurse, so you have the same structures inside, so to say. So, abstractions versus optimizations. Is it possible to have both? I guess a lot of people would say that, well, if you have micro-optimized code, if you're gonna build the fastest thing in the world, you're probably gonna need to write some sort of shitty code that can't be reasoned about and whatnot. But for maintenance reasons, you should probably have some sort of abstraction so you can reason about your code. So let's start by looking in some of the code. Is the text large enough to read for everyone? So if we take one of these value serializers I was talking about, then we have this int32 serializer, which inherits from session-aware byte requiring value serializer of int. What this does is we have this sort of code pretty similar to what Greg Young had is in his example, which says get a byte buffer and then write the value into the stream. So we take a typed object of type int32, convert it to bytes, write it to the stream that we want to serialize to. And this is actually what makes this faster than the code he had in his example. Because in the code example that Greg Young had was when he tried to convert an int32 into a byte array, there was an object allocation. He turned this int32 into a struct containing a byte array, so every time he turns its int to bytes, there will be an object allocation of bytes. What we do inside Wire is that we have this session which has a byte buffer that can be recycled between calls. And this session is not shared across threads or anything. It's unique per call to serialize. So what we can do is we say, give me a byte buffer of this size. And the size will be the size of int32, so it will be 4 bytes in this case. So we get this pre-allocated byte buffer of at least 4 bytes. And if the pre-allocated buffer aren't already 4 bytes, it will reallocate the buffer on the fly and double that, so you get a larger buffer. And what we do then is in the write implementation, we have our own class called noalloc bit converter. In standard.NET, there is a bit converter type where you can do get bytes from an int32, for example, but that will also allocate a new byte array for you. So what we do is we have copied that code, but we can send in our own byte array, which is pre-allocated, and say, take the contents of this int32 and put it into this pre-existing byte array. So we don't have a allocation per write, so to say. So this is really the first optimization that we don't need to allocate objects as we read or write because we can recycle the buffers. And also avoid boxing. If you have this abstraction with different kind of serializers, in the beginning the API only dealt with objects. It wrote objects and read objects because that was how the sort of base class looked. So if we look at this code here, and then we can take type serializer, the base type for the serializers. We have the write value, which takes an object, and then we also have read value, which returns an object. And if you're gonna read and write a lot of structs or primitives or something, that would require a lot of boxing. And boxing in .NET means that you take this value type, which lives on the stack, and then you turn it into some sort of object in the heap instead. And then you need to convert it back and forth. And that is kind of slow, at least if you do it a lot. So how can we take this API, which was defined to use just objects? We do this by actually emitting code at runtime. So instead of calling these object methods, we say that we have these typed methods which takes an int and returns an int, and then the abstraction can just take these two methods, and we can see that up here. We have the write implementation and read implementation, and we tell the base class that take these two methods, and whenever someone tries to serialize an int or read an int, inline this code in place in this code. So instead of calling through virtual methods into this base class and then using objects and whatever, we just inline the code in place to make it as quick as if you had done it yourself. And as I talked about, we do reuse buffers, and we can take a peek at the serializer session and deserializer session. So in here, we do have a buffer of type byte array, and we do pre-allocate this to the magic value of 9. And we have actually used heuristics to actually see what size is the sort of best size for this kind of objects that we want to deal with. And the reason for this is that some primitives are likely to be like 8 bytes, but we still need the type manifest saying what kind of object it is we have written to the stream. So we can serialize anything that is up to 8 bytes plus the header. So that's 9 bytes. So that would cover int64 or datetime or whatever. But if we look at this getBuffer method, we say, I want to have a buffer of this size. And if the size that we pass in is equal or less than the size of the pre-allocated buffer, you will just get the pre-allocated buffer. So we reuse this object all the time. But if you pass in a longer length, let's say it's a really big string that you need to deserialize, then we'll actually end up here saying that give me the biggest size of this, and then we reallocate the byte buffer. But we only do this in case you request a bigger buffer, and then we return it again. So that way, you mostly can reuse the byte buffer. We will recreate the byte buffer in some cases, but it will be a lot less than if you would have done it using the standard APIs and bit converter, etc. Stream abstractions. A lot of suggestions comes up when I talk about this is that, well, MS Bond and Protobuf have these stream abstractions where you can sort of write to this byte array and just send the byte array off to the stream, and that should be faster and blah, blah, blah. And it turns out that it's actually not true. if the serializer is fast enough, because if the serializer is fast enough, the overhead of sort of pooling the byte buffers in this way takes so much time that it becomes slower. So it works for all serializers that are a bit slower, but as soon as you get fast enough, then this will bring too much overhead to it. So it's a good idea in some cases, and I shouldn't say it's only in case if the serializer is slow. If you're gonna serialize a really super big object, then maybe this abstraction will be beneficial, because you could just serialize it in memory and take the entire thing and put it back to the stream. But for the sort of smallish objects, this doesn't really work. Reusing sessions. We have looked a little bit on the serializer session and deserializer sessions, where we have these buffers that we recycle. Originally, we recreated these sessions whenever you called serialize or deserialize. But it turns out that there's quite a bit of overhead of just allocating this object, because they contain this. First, we have this 9-byte buffer. We have a linked list of track types. We have a back reference to the actual serializer it belongs to. We have a list of objects that it already knows about, because we need the object identity so we don't sort of deserialize the same object twice. So it takes some time to actually allocate this stuff. In your normal line of business code, this would be completely irrelevant. But if you're gonna write a serializer and you're gonna make it fast, then if we can recycle all of this, that would be kind of neat. So what I did was, instead of always recreating the serializer session and deserializer session, you can create these individually apart from the serializer and then just pass this into the serializer. This means that even if you need to reallocate a byte buffer because you have a big string, the next time you're going to serialize an object, you already have this session with its giant byte buffer. So you don't need to reallocate anything. You can just pass in the same session and it will sort of reuse all the objects we already know about. So that made it a lot faster also. Handling exotic types. I said that we have these F# types, and another problematic library is system collections immutable from Microsoft, because they made these immutable collections which aren't serializable. So every serializer that should be able to handle this need to have some hacky code to actually know how to do this. And this is when we have the serializer, value serializer factories. And let's see if we have. Here we have one for immutable collection serializer factory. So if we have this magic type that can't really be serialized, and we don't have a reference to it in the serializer, because I don't want to have NuGet references from my serializer into each library in the entire world. So instead, we say, if the namespace and the assembly name of the type being serialized is this, then we know it's most likely, at least, inside this code. Maybe someone has made their own classes called this, but then there's their own problem. So it's unlikely that someone would call their stuff system.collections.immutable. It would be sort of crazy. So what we do, when the serializer finds a type that it doesn't know about, it will loop through this list of factories and see, can this factory produce a serializer for this type? So it will ask this factory, can you serialize this type? For example, system collections immutable list. And then we check, is it the right namespaces? Does it have the correct generic arguments and blah, blah, blah? If so, then yes, we can handle this type. And what will happen next is that we'll actually generate a serializer on the fly for it. So we have this method called build serializer, which says what type is it that we want to serialize. And then we also have a type mapping that we need to put this serializer back into, so Wire knows about this new serializer. So this code might look a little bit arcane, but it pulls out some generic arguments to know what kind of element type it is. And it also needs to know what methods to call, because there is no constructor on the generic immutable collections. You can't really just new them up. You have to call immutable.list.create or something like that. So you need to know exactly what methods to call. So in this case, we know that the methods to actually add anything to the immutable collections is create range. So we fetch that method. And then we generate the actual serialization code. So here is the code for writing an immutable list. So what it will do is actually just serialize each element as if it was an array. And the same thing when it reads the object. It will read it into an array, and once it's done reading it to an array, it will actually call the add range on the object and put the array into the immutable list. So this way you can actually serialize pretty much any type, because if you have a type that isn't supported out of the box by Wire, you can add one of these factories and say this is how to serialize this special type. And then you could control on a byte level exactly how it will be written and read from the byte stream. Another issue that I found while writing this is, let's say that you serialize a Poco class. So we have my namespace.dog might be the type name. So when we serialize this object into the stream, it will write my namespace.dog as a manifest and saying this is the type that you should deserialize. But when we deserialize, we need to read this string, which would be my namespace.dog. Then we would need to look up what type is this actually in the runtime. We would need to do a get type and pass in the name. And that turns out it's really, really slow. So the first approach to this was to build some sort of lookup where I could just have the name as a string and the result type as the value in this concurrent dictionary. So I could build up this concurrent dictionary over time. But it turned out that that is still sort of slow, because in .NET strings are UTF-16, Unicode encoded. But when you serialize something into a byte stream, you probably don't want to have each other byte as a 0, which you have in Unicode. So in order to make the string output smaller into the output, then we need to serialize it as UTF-8, which is a smaller encoding of strings. So when you read a string of UTF-8 and then want to convert that back to a string, that's really slow in .NET. So instead of mapping from string to type in my dictionary, I map from byte array into type. So I don't need to go from byte array to string and from string to type. I can just take the byte array and go there to the resulting type. And the problem we have there is that you can't really use a byte array as a key in a dictionary, because a byte array don't have a good get hash and equals method. So what I had to do there was to create this little class called byte array key. So we have this struct called byte array key containing an array of bytes. And allocating structs is really fast in .NET, so I can just create an instance of this, take the array of bytes that are read from the stream, put this into the struct, and the struct can have a decent get hash code. And in order to make that fast, then we actually only calculate the hash code when we create the struct and then just return the value, because it would be far too slow to recalculate the hash code. So this way, I can go from byte array to type lookup really, really fast. And that's also one of the tricks that makes Wire faster than most other serializers, because they read the string as bytes and then go to string and then to type. Code generation. So in order to actually make these serializers on the fly, we need to actually generate .NET bytecode. So we have this default code generator. So what it does is really that it takes all the private or public fields of the type, and then it creates a reader for each of these fields. So it will loop through all the fields in your type and see, do we already know how to serialize or deserialize this field type? If it does, then it just calls it. If it doesn't, it will have to spin up a new instance. Then we have some of the magic where we actually inline these methods we saw earlier to avoid virtual calls and to avoid boxing. So we are actually emitting code, real classes at runtime to do this, and the code will be really, really tiny. And in order to actually emit code, there are a few options in .NET. You could either use system.reflections.il emit and just emit raw bytecodes yourself, or you can use the link expressions, which is an abstraction which we got with the dynamic language runtime. And the link expressions are sort of nice to work with. It's an easy API. So that is what I used to start with when I built Wire. But it turns out that there are some security checks and overhead and etc. built into the link expressions. And they can't, for example, create instances of nested classes. So there are some limitations to that. So in order to get around that, and without recreating the entire serializer, because I didn't want to throw away the entire code base, I made this abstraction which looks like the expression API, but I actually built my own compiler into this, because why the hell not? So we have this code which sort of simulate the API of link expressions, but I can control exactly how I output the .NET IL code. And of course, I don't have to build like a full-fledged C# compiler or anything, because the only thing we do is read values and write values into byte arrays pretty much. So it's kind of small, but still it had to be done. It also turned out that it's really hard to debug IL code, so I had to make this diagnostics tools also, so I could actually see the bytecode that was generated, because otherwise you're flying blind. Some random hacks which I used in the code, which might be nice to know about, is this concept of multi-methods that I guess most .NET developers don't know about. In languages like Lisp and a lot of other dynamic languages, you have this concept of a multi-method. Instead of having virtual calls, where you sort of do a dynamic dispatch and find out what method to call, you could actually just have different methods with different signatures, and the runtime will figure out which one to use. And a problem in .NET is, let's say you have this generic type, and you want to call a method of that generic argument, but you only have the actual type in the reflection sense. Then you would have to do type create method and sort of do all sorts of expensive reflection stuff. It turns out one of the few nice use cases for dynamic in C# is that if you have a signature like this, write value of t, but we don't know what t is at compile time. We will get t passed to us in the type here. So what we can do is just take the value and cast it to dynamic, and the runtime will actually figure out that this is the correct method to call. And that will have some performance hit the first time you call it, but then it will be inlined. So it turns out that's also kind of fast if you're lazy and don't want to sort of I'll generate all the code to actually untangle this generic stuff. So that's a sort of nice trick that you could use. And it actually has some sort of nice use cases in actual line of business code, because let's say that you have some business entities, you have customer and you have employee and whatever. Let's say that you want to bind some sort of presentation logic to your business entities, and the presentation logic might not fit well into your business entities. Maybe you want to have this presentation logic sort of separated from the entities. Then you could just have this sort of present method, which takes a customer, it takes an employee and whatnot. And then you could just take your entity and cast it to dynamic and then call this present method, and the runtime will actually find out which method to actually call. So you can sort of do runtime dynamic stuff. It's kind of neat. Yeah, then that's all for me.